Okay, let's welcome Professor András Némethi from Rainier Mathematical Institute of the Hungarian Academy of Science. The title of his talk is Lattice Cohomology, the unifying construction. Let's welcome.
Thank you very much. First of all, I would like to thank the organizers for inviting me and giving the opportunity to speak here. So I would like to speak about the lattice cohomology. This is some new cohomology theory. It's a categorification. So we know that recently a lot of categorification appeared in low-dimensional topology, in categorification of the Jones polynomial, Alexander polynomial, different numerical invariants, Seiberg-Witten invariant. This is something similar, but no, it's in singularity theory or in algebraic geometry. So we categorify the delta invariant, geometric genus, and some analytic invariants. So that's the. So the talk will have three parts. The first is some introduction and motivation. After that, and also the original lattice cohomology associated with topologically the normal surface singularities. After that, I will present the analytic counterpart, and later completely algebraic context, somehow the lattice cohomology of integrally closed ideals, and so it's completely algebraic context. So let us see what is exactly, so some idea to have how we construct this cohomology theory. So all the time we will have some geometric object, say a knot or link or a surface singularity or something, or even some combinatorial setup. Then we define some lattice. We will have some naturally defined lattice, and for each lattice point we will have an integer. And somehow that defines a filter space of that, if this is, the rank is R, then to the R-dimensional space. And then using the usual cohomology of these filter spaces, we will have a bifiltered ZU module. So here what is just H0, and for H1, H2, we'll have the similar structure, and each dot basically means Z, and these are the U actions. So the U action has degree actually -1 or -2, depends how you normalize it. So that is all the time what we will construct. And of course that for this we need all these steps to follow all these steps. So let's see, yeah. So let's see, I want to present what is the main motivation for this. I started to understand, I wanted to understand normal surface singularity. This is defined over a complex number, analytic, local analytic normal surface singularities. So they are over the complex number dimension 2 with isolated singularities. So they have a link. So that link, it's in the small neighborhood of the singularity. If we intersect with a small sphere, then we will have a compact three-manifold. And that is somehow that characterizes the topological type of the singularity. So the connection is that if we consider the resolution of the normal surface singularity, as in an algebraic geometry, what we do usually, then we will have a resolution, then we combinatorial resolution graph. So we replace here the singular point by some curves, and each irreducible curve, somehow the self-intersection and then the intersection of the curves, that is codified in a graph, and that serves as a plumbing graph of the three-manifold. Yes, so that is the first connection between the low-dimensional topology and analytic type or analytic normal surface singularity. And there was a conjecture I formulated with Liviu Nicolaescu that how we connect the Seiberg-Witten invariant of the three-manifold with the geometric genus of the singularity. The geometric genus is defined by sheaf theory of the structure sheaf of the resolution, and the Seiberg-Witten invariant is a new invariant of the topology of the three-manifold. And we, for some nice singularities, for some nice analytic type, we expected that they coincide. And that was somehow the main motivation, that how to compute the Seiberg-Witten invariant, and we wanted to create somehow a theory which connects with somehow with the resolution graph, is analytic type of the singularity. And also somehow, even if we cannot, if this does not work, but at least to give an upper bound for the geometric genus. The geometric genus depends on the analytic type, so in general, only for nice analytic type can coincide with the Seiberg-Witten invariant, but we expected that should exist a good topological upper bound which somehow from the lattice points of the resolution graph and of the lattice associated with the resolution graph can be computed. And in this way, also actually one expect, or actually we defined some methods to compute the Hegar-Fleur homology for some nice manifolds, almost rational graph manifolds. So that was more or less the motivation. So let's see how we construct the lattice cohomology. So why is the lattice? Because we need a lattice. So what is important that we fix a lattice. Here the rank of the lattice is R, but also it's very important that we fix a basis. So also that somehow it's fixed. Once we have the lattice and the basis, then we consider the embedded of the lattice points in the real space, and we have a natural cube decomposition of the space. So we have the lattice points, and the lattice points plus a base element that is a segment, and so in this way the lattice plus a fixed basis gives a natural cube decomposition of the R to the R. So that's not very, of course, that it's trivial, but what is important that once we have the lattice and this cubical decomposition, then we have to introduce also a weight function, and that is the key object. So we have a weight function for any lattice points to define an integer. And that is actually should be somehow in this theory, because we want some compact support that should have a minimum. So that is a requirement. And after that, for any cube, we define the weight of the cube in such a way that is defined as the maximum of the weights of the vertices of the cube. And then we define some level sets. Sn is a space that is a union of all the cubes such that with the weight less than n. So that is a very general definition, and what is interesting that these Sn spaces might have very interesting topology. And that is basically when n is bigger and bigger, then Sn spaces are bigger and bigger, so we have a tower of spaces. So we have a sequence or filtration of the spaces, cubical complexes of RR, and we define the lattice cohomology that we consider all these spaces, the usual cohomology of these spaces, and we make this direct sum. So that is double graded. The first grading is the cohomological grading Q. The other is the homological or the weight grading, the weight grading N, Sn. And also this has a U action. U is a free variable. So we have a inclusion of Sn in Sn plus 1. And how that inclusion in the cohomology is a restriction map. So that will be for each Q, we have Sn plus or restricted to Sn gives a U action of weight degree minus 1. Yes, so that is a very complex structure, bigraded ZU module. And also in some cases we can restrict ourselves to some cubes, so it's rectangles, not all the lattice, because everything what is important in all the cases happens in the finite rectangle. So then just we repeat the definition, and the point is that it's easier to compute because you don't have to run all the infinitely many lattice points, and you have finiteness theorems. And so that is the definition. And let's see an example. So here is the rank is 2. We have the lattice points here already. I have some rectangle. And so these are the weights. And then again, what is happening that the minimum here is minus 2. So my S minus 3. So the lattice points with weight less than minus 3, that is empty. So the very first space is minus 2. So then I compute here H0. H0 of a space is exactly the connected components. So H0 I count the number of connected components. Then I have here 6 connected components, and here the minus 2 level I put Z, 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 so that 6 dots. Then after that, the level minus 1. So if I have a segment and both endpoints have weight less than minus 1, then I consider the segment, otherwise not. So for example, this segment is not good in S minus 1. So this is the space S minus 1. This is connected, so that means that here in H0 I have a Z. And also the U action, how the minus 2s are included, yes, in this S1 space, that is basically the U action. So that inclusions, yes, of the tower, that is measured by that U action. But also here I have a cycle, one cycle, and that is H1 at the level minus 1 appeared. Yeah. So then again we go to the next, that is H0. H0 here, I have these old components, that is a bigger one, but it's connected. But two more components appeared, and that is I have at H0. H0 at this level is 3 Z, Z, Z. And also the one cycle is killed, disappears, so here it's nothing. That is the U action that disappeared at the level 0. And after that, here in this case, we can continue, and that will be connected. I have only one Z, and after that, nothing important happens. So I will put my. So I don't know. Yeah. So that is no H0, that is the H1, and the degrees and the U action. So you see, we have a lot of structure inside of this. It's codified. This cohomology codifies a lot of structure, and is rather different than, say, any other cohomology. Actually, it has the same shape, same nature than the Hegar-Fleur or monopole, yes, or even has more grading than the Hegar-Fleur. So let's see an example, topological lattice cohomology. So what is important here, that how you define the weight function. Of course, that you can define the weight function for any lattice points. You put some number there and you have a lattice cohomology. But the point is that if that is good for anything, so if it's that really it can be connected with the geometry of that object what you want to study. Here, and one more important object is that is for very generally you can define the Euler characteristic of the lattice cohomology, and then yes, you can define also the reduced lattice cohomology when you consider the reduced cohomology of the S-n spaces. And in this way, that is just the classical definition, but here you have to modify a little bit the definition, and that is the Euler characteristic. And the first step, or the first test, that if your lattice cohomology is a good one or not, if the Euler characteristic it's a good numerical invariant. In that way, you can say that you categorize, say that numerical invariant. So let's see. I start again with a normal surface singularity, and I assume that the link is rational homology sphere. It's not so important, but technically it's I use it, and so that means that all the exceptional divisors are rational, and then the graph is a tree, and then very naturally, we have a lattice because we consider H2 of the resolution, and that is generated by the exceptional curves. The exceptional curves are Riemann surfaces, so their class, homological class, it's a natural basis for this lattice. We have an intersection matrix there, a negative definite intersection matrix. So then the next is how we define a weight function. In this case, I choose the weight function, the Riemann-Roch function. Actually, this is originally defined as an analytic cohomology Euler characteristic, but by Riemann-Roch theorem, actually it's a minus sign is missing here. By the Riemann-Roch theorem, that is topological because this is the canonical cycle. The canonical cycle can be computed using the junction formula just from the intersection matrix, so that is completely from the resolution graph or from the lattice you can recover. So that is associated with this lattice, we have this number, which is somehow comes, yes, from the geometry from Riemann-Roch theorem. L is a lattice point. L is a lattice point of this L. This L you ask? Yeah, so it's for any lattice point, yes, I consider, yes, for any divisor, say positive divisor, you consider the Riemann-Roch of yes. So it's rational homology sphere, and here then, yes, and you have the canonical cycle, and that's exactly the Riemann-Roch formula, and you define for any divisor, you introduce this expression. And that's the way. The singularity is not rational. No, yeah, it's definitely clear. Yes, definitely. That is important because exactly we will see that the singularity is rational if and only if the lattice homology is trivial. That's exactly one somehow theorem. Yes, but the singularity is not rational. Yes, that's very good remark. So in this way, we define this weight function. Of course, that again, the question is that if this it can be connected with anything from what we know about the singularity or from the topology of the singularity. The first result is that this object is independent of the choice of the resolution. So that's very important because here I fix the resolution. Also the lattice depends. Also the Riemann, everything depends on the resolution. You have to show that if you blow up or blow down, you choose another resolution, then this invariant is the same. That can be proved. So this means that this invariant is just the invariant of the link, yes, of the D3 manifold. So then we can ask that if we can connect with any invariant of the topological invariant of the link of the 3 manifold, and then indeed it's true. First of all, it's H0 gives an upper bound for the geometric genus for any analytic type of what you have on this topological type. So that is a topological upper bound for the geometric genus. And also the Euler characteristic of the lattice homology of the link actually is the normalized Seiberg-Witten invariant. So that is exactly the number of exceptional divisors. That is Kx is the canonical class. One can show that this is independent of the resolution. That is just the link. So actually, in this way, we hit a very important numerical topological invariant as Euler characteristic, and it's a categorification of that Seiberg-Witten invariant. Of course, and then we can ask that there is another categorification, the Hegar-Fleur, and what is the connection? And actually, that was one of the motivations, that how in this way we can recover somehow the Hegar-Fleur. Yes, please. Yes, that is the second homology. So the capital L, so you have the resolution. Yeah, so OL, so what is, you have the resolution, so you have, so that is the resolution. You have, that is the union of EIs or EVs, yes. So these are the curves, yes, so that each of them, so the lattice is generated by these EVs, yes. And then it's an L is a sum of N VEV, and you can consider also also as a lattice point, but also as a divisor. So when I write OL, that means exactly the structure sheaf of that divisor. No, it's here I consider, you see, that's why I told that sometimes we consider some rectangles, or for 0, I define as 0, and for positive, I define by Riemann-Roch. So that is I define for R positive. And and this is, and we know that this in general by Riemann-Roch is minus L minus ZK. So that is the intersection form, and actually this formula makes sense for any L if you wish. So not just, but this is the geometric interpretation, or that is the idea why we define it that way. No, if it's, no, all the time I take this expression. Always I take that expression. If L is 0, then it's 0. If it's but basically I want only for positive, so for effective cycles, it's enough. Actually, there is a theorem that you can take for complete lattice with this one, or you take the first quadrant with this one. They, Sn will have the same homotopy types, so the same cohomology. Even more, immediately we see that even you can take a rectangle, finite rectangle, we see here with 0 and here the zk, the canonical class. So, yeah. So it's very amazing. Just we take this one and we make that combinatorial elementary something, and we hit exactly the Seiberg-Witten invariant of the link. So So let's see some connection with the Hegar-Fleur. So there was a airspace conjecture in the theory of three manifolds that actually that was the link or the three manifold is Hegar-Fleur airspace. So that means the Hegar-Fleur homology is trivial if and only if the fundamental group of that link is not left orderable. And that was for graph manifold was proved by Hanselman, Rasmussen, and Watson. And here, in our case, in singularity theory, all these are negative definite graph manifolds. So that already was proved, yes. And I use that one, and also my theory of lattice cohomology that is equivalent with the link is airspace if and only if the lattice cohomology is trivial, if and only if X is rational in the sense what you asked. So that means exactly rationality. We can characterize rationality using the lattice cohomology of the link, or we can even elliptic. It's elliptic or minimal elliptic in the Lawfare sense. We can characterize using the lattice cohomology. And that is just somehow the top of this discussion, that this triviality, equivalent with this triviality, actually follows from this theorem. I conjecture that the lattice cohomology is the same as the Hegar-Fleur, and in many cases I proved. And for almost rational or for star-shaped graph, and there's one bad vertex, yes. But in general, was proved recently by Zemke that the topological lattice cohomology is the same as the Hegar-Fleur. And we have here also some structure theorems that basically the SN space, it's all the time connected for n positive. So basically what is happening that you have that is the weights, and we have somehow the minimum of this Riemann-Roch expression, we have 0, and here all the time it's just connected. Yes, it's just connected that we have a bamboo of these, but what is important, it's exactly this zone. So there you can have some very interesting structure, but you have this, it's the weights of the lattice cohomology are between the non-trivial part is between the minimum of W and 0. And also we have a reduction theorem that sometimes you can reduce the rank of the lattice. For example, in the case of singularities, if you can just say the set of nodes, and then you have to redefine in the somehow interesting way the weight function, and then you will have a smaller rank and computation that can be very important. For example, in the case of star-shaped resolution graphs, then the rank is just 1, and then it's much easier computation. Okay, so let's see now just some of what we have now. So that was the original definition, but so here what I want that this is the dimension of the singularity, dimension 1, dimension 2, higher dimension. So these are the curves, these are the surface singularities, and this is the topological analytic, and this is later I speak about the algebraic context, and that is the Hegar-Fleur. So somehow this is the table, and just what I explained is this part, the topological lattice cohomology of the normal surface singularities, and that is the connection with the Hegar-Fleur. Actually, this has some graded version or filtered version also, which can be linked with the Hegar-Fleur link homology. But for me, exactly how I explained that what was the motivation that to connect the Seiberg-Witten invariance, so the Euler characteristic of this with the geometric genus, was a very important question, that is there any analog, analytic analog of the topological lattice cohomology which categorifies the geometric genus? Just from the analytic type, so not from the resolution graph, not combinatorially, from the analytic type to define something similar, which is it's a double-graded ZU module whose homology, whose Euler characteristic is exactly the geometric genus. And that can be defined, and actually can be defined in any dimension. But here, what we use here is we use the resolution, and here we use the normalization. And now I will present this and this example, and a little bit later, the completely abstract algebraic context also. And here now again, we can make the next question that we started with the topology here. We generalized to the analytic part. The analytic part has a natural generalization to any dimension. Then we can go back. Is there any higher dimensional analog of the topological lattice cohomology? And that is still a question mark. And yeah, so I can comment, but let's so let's see now what is the first step, or what is the structure for the analytic lattice cohomology? It's first I present a combinatorial setup. So again, what do we want? We have a rectangle or maybe a complete lattice. We have with fixed bases, and we want to define the weight function. And we define the weight function as a sum of two other functions. So these two functions, H and H circle, and with the following property: one of them is increasing, the other one is decreasing. And of course, that they are defined somehow geometrically, and with some properties. And then we combine them, we make the sum. That is an example sometimes when somehow we have a geometry behind this Gorenstein or some symmetry we have, then we can even take the second function as symmetrize the first function. And then what is the point? That if this pair satisfies some combinatorial properties, some combinatorial duality and matroid rank inequalities, I will not be very precise about this. Then we know that if we construct in this way the lattice cohomology, then the Euler characteristic it has this formula. So that means that even when we want to categorize something, some numerical invariant, then we have some hint that what kind of functions we should take, or at least we have some kind of, yes. So that is some kind of codimension. We will see in examples so that means that it's something increasing, that h of R plus any base element is bigger than h of R for any V and any L. Yes, so it's, yeah. So let's see how it works for the analytic lattice cohomology of normal surface singularity. So again, I start with a complex analytic normal surface singularity. I assume for simplicity that it's the rational homology sphere, the link. It's not really necessary, but let's assume. And I want to somehow to categorize the geometric genus. Originally, the geometric genus is defined as the H1 of the structure sheaf of the resolution. But now, using Laufer duality, I will use this formula because it's then easier to explain this construction. So again, I have the lattice as before, H2 of the resolution. We have a very natural fixed basis given by the exceptional curves. And then I want to define the weight function. And again, as in the general recipe, in this way, I need two functions. That is just a normalization in this way. V of 0 is 0. So I need two functions, and both of them are Hilbert functions. Hilbert functions of some filtered filtrations of some modules or rings. So first of all, we consider all the functions, yes? All the functions, and then we consider the divisorial filtration associated with the divisors, with the resolution. So for any lattice point, I consider all the functions with at least vanishing along the exceptional divisor at least L. So that is the filtration. Yes, L indexed multi-value variable filtration of the ring of functions. Yes, so that is the first one, the filtration. We consider the corresponding Hilbert function, and that is the HL. And then we consider the holomorphic two forms on the resolution with pose along the exceptional divisor. And then also that one will have a corresponding divisorial filtration, and that gives again, has a Hilbert function, and that is the second function. And then we consider the analytic, so the weight function, the sum of them, and then we have a lattice cohomology. And the point is that, again, the question is that if we made this definition, if this is good or not. And this is the theorem, that if in this way, if we define the lattice cohomology, then first of all, it's independent of all the choices. So if I take another representative, Stein representative, and the resolution, then it will be the same. or if I take a different resolution, I blow up, yes, then it's, again, that is independent of the choice of the resolution. The second one can be computed in a rectangle. That is the cohomological cycle. Maybe you are familiar with it, or if not, then again, you can take this one. Usually the cohomological cycle is even smaller than this one. So it can be computed in a finite rectangle. Most importantly, that the Euler characteristic of this lattice cohomology is exactly the PG, what we wanted. So this is a good sign. And then the point is that this, what I explained here, it can be extended for any dimension, higher dimension. We have resolution, we have divisorial filtration, Hilbert functions, top holomorphic forms with poles. We make the filtrations, the multi-wave filtrations, the weight function, and we have the lattice cohomology. What is important here, that this is in the spirit that what I wanted, that how we compare, say, the geometric genus and the Seiberg-Witten, that we can compare now the two cohomologies, the analytic cohomology and the topological one. This depends on the link. So say we fix a topological type, and we fix the link, the three manifold, that has a, say, the Hegar-Fleur or the lattice, topological lattice cohomology. And then for any analytic type, any analytic realization, gives another lattice cohomology, bigraded ZU module. And then you have a natural map that can be proved. And there is a conjecture that I conjecture that should be injective. So somehow the possible embeddings of this, yes, so that gives somehow a hint that what kind of analytic structures might appear on the fixed topological type. In general, it's very difficult to analyze or to describe the moduli space of the analytic structures. This. So that is the lattice cohomology of the topological lattice cohomology of the link. Yeah, that was the notation of the. Yeah. So let's see. So that's how you define. Yes. So that is the lattice cohomology. Yes. So that is the bigraded ZU module. So that is this I use as a lattice cohomology of. And that is the lattice cohomology. Yes. So that is. So that is associated with the link. That is the first construction using the Riemann-Roch. But that is associated with the weight function of the topological weight function, with the Riemann-Roch function. And that is the lattice cohomology associated with a different weight function, which is associated with the analytic type, with the Hilbert function of the divisorial filtration. So that measures really the analytic type. So that is from the Hilbert functions. And that is just the link, that is the resolution graph. The name lattice, because I defined the lattice, I defined the weight function of the lattice, the construction is the same, but I changed the weight function. Here I define the weight function using the topology of the resolution graph. Here I use a weight function from a Hilbert function of the local ring, of the divisorial filtration of the local ring and differential holomorphic differential forms. Well, immediately, yes. So that is the conjecture that is injective. Immediately, so let's see. So here is, for example, this is a topological type. So that is a negative definite intersection form. So that can be realized by singularity. Actually, that link now is that M, that L is, if you, I don't know if you prefer, that is S3 minus 1, the 2, 3, 2, 3. So that if in topological language, that is the link. That has, say, a Hegar-Fleur or has topological lattice cohomology. And that actually has also an H1, but this is a H0. So we have minus 1, 2 components Z, 1 component, 3 components, that is the U action. So that is the graded ZU module H0 of the topological type. And now there are many analytic types. So it's, of course, that only, yes, those singularities which have only one analytic type, they are the top singularities classified by Laufer. That is a very restrictive family. So this has many analytic realizations. One of them is a Gorenstein, actually is a complete intersection, is a splice type. The other is a Kulikov construction, and this is the generic one. The geometric genus can be 3, or 2. And even you have families, moduli. And you compute for all of them, and you see it's different. So the lattice cohomologies of the analytic realizations are different. Here, actually, this cycle corresponds to the Artin cycle in the lattice, and here the minimal, so the generic hyperplane section, the maximal ideal cycle is not the Artin cycle, so that is missing. Here, the Gorenstein, that is the ZK, which is the canonical class, that is missing. So that shows that this is not symmetric, it's not Gorenstein, it's not Gorenstein. That is the generic one, that is the smallest one. So you really see in the analytic realization, analytic lattice cohomology, you see that somehow a discrete, it's a very important discrete invariant of the analytic type. I don't know if there is any question about this before I start the... So it's a completely new type of invariant of singularities. And let's see the curve case. In the curve case, you don't have the resolution, but you have a normalization. So we start with a reduced curve singularity, not necessarily plane curve. So can be the embedded dimension can be anything. So of course that we can consider also plane curves, and we can see that what are the particular properties. But let's completely general. Reduced curve singularity, usually it's very hard to classify them. We don't really know what to do with them. And that is the locally reducible decomposition. We consider the normalization. Each curve Ci normalized is smooth, and that is the ring of functions, yes, on the normalization. And the codimension of O in OC bar, that is the delta invariant, the Serre invariant. That is the most important numerical invariant, yes, of a curve singularity. Yes, so if you think about the semigroup, that is exactly the number of gaps of the semigroup, if it's irreducible, for example. Then again, I want to define a similar strategy. I want to use a similar strategy. I want the two functions, and then I make the sum of them, and that will be the weight function. The one of them is again, we have here valuations. So that is the valuation associated with the normalization. We have not the divisorial filtration, but the filtration associated with valuations. And then the corresponding Hilbert function, that is the usual Hilbert function, is yes, of the singularity. What is here the lattice? The lattice exactly generated. If this has R components, then Z to the R. Yes. So we have the normalization, and each integer Li associated with Ci normalized gives a valuation, and then we have the filtration, and we have the Hilbert function. And then we consider again here some differential forms. They are the Rosenlich differential forms, yes. So they are, usually we consider forms on the normalization with arbitrary poles, and then using this formula we define some special submodule of meromorphic one forms, and they are called the Rosenlich differential forms. That is classically was introduced, and also Serre considered, and on those forms, again, we have the valuations the very same way, and we have the corresponding Hilbert function. So we have some duality again between the two Hilbert functions, and then we have we define them using the valuations, and we define the weight function in this way. And then again, what we have that again, that is a well-defined invariant of the curve singularity. So this lattice, R is the number of irreducible components. The weight function is defined in this way of the combination of the two Hilbert functions. This can be computed in the finite rectangle where this is the conductor of the curve singularity. And the Euler characteristic is the Euler characteristic is the delta invariant. So here we have one more additional property, what is very important, and actually that's the goal. That was why we wanted to understand. So usually when we have a cohomology theory, then to an object you define, say, the homological group. And also you need the morphisms. And in the topology we have the functions between topological spaces, continuous function, then you have a functor. In the Hegel-Fleur or in this monopole cohomology, you have, if you have a cobordism, then that induces a morphism between the groups. Here in the case of normal surface singularities, I was not able to define the morphism, but in the case of curves, it was possible, and that corresponds. So here the cobordism cannot be, that is not analytic, yes, and here this is an analytic theory, but it's a flat deformation. That corresponds to the cobordism. So if you have a flat deformation of the objects, then you expect to have a morphism of these bigraded ZU modules. And that's exactly what happens. Here we succeeded to prove for the H0 level, but conjecture is that U is a variable. That is the U action, what I told you that Sn is included in Sn plus 1. So the lattice cohomology is the direct sum of HQ of Sn Z, yes? And then you have Sn included in Sn plus 1. So that means, and that is the tower. Then you have HQ of Sn plus 1. Z, you have a natural map to HQ of Sn Z. And that is the U action. So on this one, you have a shift, yes. And that just, in the topology, it was denoted in the Hegel-Fleur theory by U, and then even earlier by, so that is in physics was, it's a classical notation. We just keep the U. So that is the, if I have this graded root, or yes, if I have this, then this action. So this, actually in this cohomology is this way. So this generator goes in this plus this generator, this plus this generator. So it's very, so you see in general the deformation of curves it's an open problem. Even for plane curves, we don't understand that what topological type or analytic type can be deformed in other ones. So that was already studied by Arnold's school and still an open problem. It's a very hard problem. But here it's because the cohomology is so rich, then we can have a chance that maybe we can classify that we have a bigraded U action, then maybe that gives some, yes, some restrictions, or that just numerical invariance in this problem, you cannot solve the problem. But using a very, very rich invariant, that maybe it's a possibility. So for example, I have this deformation of curves, and then these are for T's 0 and T non-zero, the corresponding graded roots, and then in this case we have the morphism, which preserves the U action, and it's generally it's not injective, not surjective, but still it's a complicated morphism what can be analyzed, and that gives a hint that if sometimes you have that such a morphism cannot exist, so that means that some deformation cannot exist. So let's repeat again a little bit what we have, because I want to define now. This was defined for singularities, but no, I just want to go in the general context for any algebra or for any ring or for any ideal to define the lattice cohomology. What was important? So we had a lattice in both cases, the curve case and the normal surface singularity case. We had a lattice with the basis, very naturally that geometrically identified. And we have in the ring of functions, we have some valuations, and that gives that has a multivariable valuation. So here is a divisorial one, and that gives a Hilbert function. The same is here. Also, we have a module. Yes, we have a module, and also the module has somehow valuations, extended valuations, and then corresponding Hilbert function. And then we consider the sum of the two functions, that is the weight. function that defines an Euler characteristic that defines a lattice cohomology, and the Euler characteristic of that is somehow this dimension of this quotient. So that is the module M, and that is a submodule. That is here the submodule of regular differential forms. Exactly the same here. So what we have that. So in both cases, what we have, and that will be the general context, that we have a ring. We have a ring. Then that has some filtrations. Then we have an O module, yes, and that also has some filtrations. And also we have somehow a submodule, and then that is given by that f of M0. Yes, and then and what we have in both cases, that somehow we have a homology theory, the lattice cohomology, which is the Euler, so that defines the lattice cohomology, and what is the important part in both cases, that the Euler characteristic actually is the dimension of M over N. So in both cases, somehow this is happening. That is the general strategy of what we want to follow, the next construction. Is there any question about this? So let's see the general context. Then again, we have a field. We consider a K algebra, which can be finitely generated or even a theorem, but all these are not so important. And what we have, that we have also, M is a module, and we have valuations. Yes, a set of valuations on the ring. Actually, this is extended or generalized valuation. In this case, it can happen that if we have valuations, so it's, say, that is a prime idea, so it's not necessarily zero. So it's, yeah, so we have a set of valuations on O, we have a set of valuations on the module, and we have some kind of compatibility. That is the condition A. And then for both of them, using the valuations, we consider the filtration, the associated filtrations, and the Hilbert functions of filtration of O, the filtrations of the module. And also, we concentrate exactly on this property. So exactly this context now, we have filtration. The codimensions are the H, the first function here, the second function, we have the weight function, and we have a lattice cohomology. And we want to see what is exactly this. And the most important theorem is this theorem, proved with my student Scheffler, Gergő, that if we fix this context, that O, M, and the submodule in M, and then if we find some discrete valuations such that compatible, yes, or the first one is the second one, in such a way that M is cut out exactly by these variations, then the lattice cohomology, which is constructed using these valuations, with these filtrations associated with the valuations, that is independent of the choice of the valuations. So for example, if you take a curve singularity, the curve singularity, you can take two natural filtrations or valuations. That we go to the normalization, and then in normalization you have the natural valuation. But also say the curve singularity is a Newton non-degenerate, then you have the Newton diagram, and the faces of the Newton diagram give a valuation of the monomials, and you have a monomial valuation, and you have a natural, and both of them provide a lattice cohomology. The point is that the weights are different, but the lattice cohomology will be the same. The weights. So if you consider the Hilbert function associated with the normalization, even the number of yeah, so it's even the number of the rank of the lattice can be defined. So that means that if we are in this situation, then if this n can be realized as a cut out by a set of evaluations, then this has a lattice homology associated with the realization of using the set of evaluations, but that is independent of the choice of the valuations. What still I have? That means, okay. So that is this theorem that basically what we have, that if we have, so let's see what is the meaning that is realizable, a module, submodule is realizable, if I can find, yes, if we can find, so maybe it was here. So if something is realizable, if we can find a set of valuations such that n is cut out by those valuations. Actually, it's we know that the valuation theory that more or less is the same as the integrally closed. In the sense of Ries, if it's a submodule is integrally closed in sense of Ries, then it satisfies this one. Or it's, for example, an ideal. In the case of ideal, that means exactly that is integrally closed ideal. So that means that if in those cases that if a submodule is integrally closed in the sense of Ries, then you take one realization, somehow a set of evaluations that is not unique, and then using that set of evaluations, then you have a lattice, you have a filtration, you have weight function, you have a lattice homology, but that is independent of the choice of the valuations. That depends only on the despair. And the Euler characteristic actually of that homology is it's exactly the codimension of that idea. So that is somehow the categorification of m over n, of the dimension of modules of submodule m over n, and when n is cut out by a set of valuations, so integrally closed. So let's say, for example, in our cases, in the case of curves, that is exactly we take the differential forms, the Rosenlich differential forms, and this is the regular differential forms, and that pair, the lattice homology of that pair is exactly the lattice homology of C of the curve. And here the differential, yes, meromorphic, or yes, meromorphic differential, top differential forms on the resolution, and this is a submodule of the regular ones. That pair has a lattice homology because that is exactly cut out by the divisorial filtration, yes, and then that is a lattice homology of the analytic of the normal surface singularity. In this way, actually, you can extend even higher dimension. This is exactly the same. You can take the irregularity when we take here instead of omega 2, take omega 1. Yes, to take the omega 1 differential holomorphic 1 forms, or in higher dimension, you can take the top forms of top minus 1 forms, and then you have, again, categorification. You have for the plurigenera, when you take the top forms on the power, m power, you can have equivariant version. So it's all the geometric situations more or less have this type of structure, and they all have categorification, lattice homology categorification. So again, we have this connectivity, exactly this picture what I show here in the case of that particular case. In this general context, it's true. That is again proved by Kubash and my students Kubash and Scheffler. And also we have a reduction theorem. Sometimes you can reduce to the smaller lattice. So let's see just in a few minutes what's happening in the case of ideals. So again, what is happening, I take an arbitrary ring, and I take the module exactly that ring, yes? So in this case, we have O, and M is O, and we need a submodule, of course, that is an ideal. So that is the context in this case. Again, this should be cut out by by evaluations. So that means that this ideal is integrally closed. So that's exactly the situation. And we want finite codimensional. So in the case of this context, is I have a finite codimensional integrally closed ideal. And then we can define the lattice homology. It turns out that this lattice homology actually is symmetric. why it's actually, it's also here we feel a little bit, because what is the meaning? That usually what we used here, this was somehow a dual, the differential form. So that is the dualizing sheaf, if it's rank 1 free, that means somehow Gorenstein property, and that means symmetry. So that means that you have a Z2 symmetry of the theory, and also on the lattice cohomology, you have a involution. And so that can be defined, is well defined in this context. Any integrally closed finite codimensional idea has a lattice cohomology. So, cohomology is product. Well, in this sense you have, but I didn't really, yes, so they have. So each piece here, there is, yes. So you can, but I don't know, I didn't study yet that one, but you have it. And even you have more, that you have, even you have the SN spaces. So any, even cohomological operators and everything. So what you have for a given space, what you can do with cohomology theory, you can repeat. Because it was a graded version of this, for all this tower of spaces. Yes. So for example, in this case, because if we have R valuations, then everything is in R, yes, and this is the space Sn, then this means that here HQ of Sn Z is 0 if Q is bigger than N. So that is actually, it's a property of this, that means that we have some kind of measure that how many evaluations we need to cut out the ideal I. So if this is HQ is non-zero, is this lattice cohomology you have, it is automatically is associated with the ideal, independently of how you choose the evaluations. That this means that if this is non-zero, then you need at least Q plus 1 valuations. So actually, I don't know if, so usually it's very, very hard to decide that if it's something you have an integrally closed idea, how many evaluations you need. And actually, this number can be smaller than the number of risk evaluations. The risk evaluation is fixed, so that we know that what is that. But that can be smaller. For example, we have the conjecture that if this is for, so only H0 is concentrated everything in the lattice cohomology H0, then the ideal can be identified, can be cut out by a single valuation. And in all examples, what we consider this is true, even if the number of risk valuation is higher. So it's, yeah, so in this way, what we have that for actually it's a second theorem is that actually it's not just the pair is important. What is important, actually it's just the corresponding art in algebra. So if you fix the art in algebra, doesn't matter how you identify, how you express in this way as I integrally closed, that has a lattice cohomology independently of all the choices. So any art in algebra has a lattice cohomology. So for example, in this case, in the case of curves, again, let's reconsider in this way. We have the conductor ideal of the curves, and actually this conductor ideal inside of the local ring, that the lattice cohomology of that is the lattice cohomology of the curve. In the Gorenstein normal surface singulated, that is a joint idea. We have a classically defined joint idea, and using the canonical class, so that is the joint idea, you know, X, that has a lattice cohomology, and that is the same as this one. Also, in the case of Newton non-degenerate singularities, you have the monomial idea associated with the Newton diagram, that is that one, and you have the associated joint idea, and the lattice cohomology associated with that, that is the analytic lattice cohomology of the curve, or even higher dimension, that is in any dimension is true. So that also shows that somehow, if I define in higher dimensions, say using the resolution, or in the curve case using the normalization, or if I use the Newton diagram, I get the same lattice cohomology. It's independent of how the different valuations are defined. In this way, yeah. Why is this important that we can reduce everything to the ideal? Is this new property, say, or new conceptual definition that we have many different properties or families of deformations, that delta constant, PG constant, K constant, so it's different versions of or families of deformations. Here, if the say the ideal or the conductor ideal is constant, or the joint ideal is constant, then automatically we will have that the analytic lattice cohomology is constant. So you take a deformation, and then, of course, that's exactly what we wanted there to understand it, what is happening along the deformations. Then in some cases that is constant. It's not true. At the beginning we saw that, for example, in the case of curves, if you have a delta constant deformation, then that should be constant. It's not true. And probably that's good that it's not true, because then that really tests. So that means that you have a rich structure. But so I don't know if, so maybe I'll just stop here. Thank you.
Thank you for the great talk. Is there any question from the audience?
So if you have a normal surface singularity and like a curve going through it, you have a link in a three manifold.
Yeah.
And then can you...
Yeah,
how you got
there is
Fleur?
I said nothing about that, but it's on the archive. There is a filtered version of that you have a normal surface singularity, you have a link on it, and then you can consider somehow the filtered or the relative version. Yes, it's done. And then that is, you can connect with link Hegar-Fleur or yes. And also in the case of curve case, if the curve is embedded in C2, then again you can connect with the filtered version of it, you can connect with the Hegar-Fleur link. So yes, it's a very natural and great question, yes. But it's, I don't say that everything is completely done, but it's some versions are, yes.
Other question?
Hi, thank you very much for the talk. As far as I understand, the basic setup for this lattice cohomology is you have the filtration of topological spaces,
Yes.
and then you apply cohomology.
Yes.
And so this is the same basic framework that is used in persistent homology in topological data analysis.
Yeah,
I wondered if you thought about this.
Yeah, that's a different version. But here, what is really important is that somehow a user weight function, which is given by the geometry of the, say, a resolution or by analytic type or yes, and then I associate this as Sn, and then of course then you have this tower of spaces and you have the corresponding cohomology. That is somehow similar, but what is the weight function here? That I won't say to categorify the Alexander polynomial. Well, give the weight function, yes? So that's not, find the filtration. So that's the point. Find the filtration.
Yes. So
yes.
I wondered if, I mean...
Yeah, but you are completely right. It's the same, yes.
If you at least have coefficients in a field, then you have these other tools, such as interleaving distances between persistence modules and things. I wondered if they might be useful in your context.
Yeah.
But, oh, okay, thank you very much.
Yeah, thank you for your nice talk. There are many different kind of singularities, like quotient singularities, or low canonical, Dubois.
Yes. So,
your theory can be used to...
yes. Maybe just... so the point is, this is one of the theorems here that... so in the case of, if it's, say, normal surface singularity case, if X is rational, then that is equivalent that Sn is empty if n is negative, and is contractible if n is positive. So that is exactly the simplest case. So that means that your spaces here is level 0, 1, 2, and this is it's contractible, that is in H0, only H0 survives, no other cohomology, and that is a Z, 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 and that is the inclusions, yes, that is included in that, yes. And so basically that is what you have, this is the structure of H0. And so for all rationals, so all in the case of normal surface singularities, then all the quotients, the singularities have this one. In higher dimension, I didn't check yet that what is then the rationality can be characterized. So in this sense, you can say that, okay, this is not so important in the case of terminal or I don't know, the quotient singularities. But the point is that you can take exactly what you asked, that you can take the filtered version of this. So it might happen that your space is indeed somehow connected, say of this shape, but if you take a filtered version of it, then you will have, and then you have a spectral sequence, and the E1 page of that has a lot of information. Even for quotients, even for AN or very simple singularities, you have a filter version, an extra filter version of this, and then you have a spectral sequence, and the pages of the spectral sequence have very, very important information. And that can be connected with, say, classical invariance of quotient if you can recover. So, for example, in the case of curves, you can recover, so you can connect with the motivic Poincare multivariable Poincare series of the curve, or even if it's plane curve. You see, so indeed, so in this what I explained, just non-filtered, so it's this version of the naive version, say, of the first version of the lattice cohomology for quotient singularities is not so interesting because it's this one. It's a bamboo. But you make one more step.
Yeah, how about elliptic singularity? For example?
No, the elliptic singularity, it's again, so it's the minimal elliptic singularity of Laufer has this shape. So, and yes, so that is the zero cycle, and that is the elliptic cycle. That is the minimal elliptic. Or the general elliptic singularity, that is the level 0. Then this is, you have here more, and this is connected. Here we know that starting from 1 should. And that is how many you have. That is the length of the elliptic sequence in the sense of Yau, Laufer, Stevan Yau. And so then again, you see all the important numerical invariants of the elliptic singularities. So somehow all the rationals of this, all the elliptic on these ones, and if indeed if you introduce one more refinement, the filtration given by the degree, then you will have a spectral sequence, and that contains even more information. So that is somehow, I think that, you see, that somehow the classification of singularities was stopped after the elliptic, because it was not so clear that what is the combinatorial skeleton, what you have to use. Yeah, because here was the sequence of Yau sequence was important in the elliptic case, but in the more complicated singularities was not clear. Well, this is the skeleton what one should use for the classification of singularities. That's what I believe. But
Thank you.
Other question? Okay, let's thank speaker again.